Greetings, friends. My name is John Gabriel, and today I'm feeling exceptionally well after a good night's sleep. Wish I could feel like this every day. Unfortunately, I don't, but I'm able to think pretty well this morning, and I'd like to discuss a topic that I've discussed quite a few times in the past. In fact, probably about 5% of my videos cover this topic, but I'm going to once again show you a different perspective and explain to you what exactly does it mean to be a number. So let's begin. Now, what is the precise definition of number? Now, let's see. I have never actually met any mathematics professor or teacher who actually understood the concept. Now, this guy here, Professor Edwin Clements, claimed in one of his articles on the site academia.com that number, coming to the realization that the notion of number is a difficult, if not impossible, idea to define precisely. And that kind of proves my point. It proves what I've always said, that mainstream academics have never understood the concept of number. And I'll prove to you in a little while that this claim is false. But the reason they haven't understood is due to the fact that they've never understood the elements of Euclid and what Euclid was attempting to do in the elements. Now, we can go right to the beginning. Well, this isn't actually the beginning. This is probably several books into the elements. But what comes before book 7, which is what you see in front of you, the first definition, is a whole construction of the geometry, of ratios, and everything else that is needed so that the definition of number can begin. But now, so what does Euclid say in the ancient Greek, which is written in red? He says, monas estin kath in ekaston ton ondon en leiete. Now, it's much easier to translate that to modern Greek, which is in the blue, which says, monada ine αυτό που κάθε ekaston ton ondon leiete. And what it really means is a unit is that which every being is called. Now, that statement in itself is very difficult to understand if you don't know what came before that, all the machinery that was in place before Euclid made that statement. So I'm going to explain to you in a second now what comes before that and why Euclid said that. So let's continue. The definition of a unit leaves out many details because Euclid assumed that the erudite academics of his time understood the purpose of his work. In other words, to derive a perfect formulation of the number concept. Euclid treats the unit in an abstract way in that previous definition that I just read to you, disregarding not only its size, but also homogeneity. Okay, what is homogeneity? When two things are the same. He makes the transition in book 7 from discussing measure in geometry to generic measure, which is the core concept of algebra. So let's see an example. Now, consider any two right-angled isosceles triangles. As you see in the picture here, here's one with a red hypotenuse and one with a blue hypotenuse. Which of these hypotenuses is the real square root 2? Think about that. Okay, you can't say either of them are the real square root 2 because the units in both cases are different. You can only realize the hypotenuse by using the equal leg, either one of the equal legs in either of the triangles. There's no other way to realize square root 2. Okay? And in geometry, you can do exact measures. For example, you can measure the hypotenuse with a leg. As I've shown you before, you can say, well, if the hypotenuse is 3 units, as you see over here, if the leg is 3 units, as you see over there, okay, and then the hypotenuse is this red line here, and of course this red line divided by the hypotenuse is square root 2. Okay, so you can do exact measurement. Well, it's square root 2 according to this unit, all right? But in algebra, you don't care anymore about the unit size. There is no, the abstract unit doesn't worry about size whatsoever. You can have any size you like. It's just a case of using it to describe every other number, okay? So now, as I've just said, in geometry, it all depends on which leg one chooses as a standard of measure, that is the unit. However, in algebra, the unit size does not matter, so that the measure of the hypotenuse using either leg 3 or 5 will yield the same result. So if in one triangle you say 3 times square root 2 divided by 3, and 5 times square root 2 divided by 5, you'll get square root 2, right? So the operation of division, by the way, is a measure of the dividend, which is the hypotenuse, using the divisor, which is either of the legs in one of the triangles, as the measuring stick or the tape. In geometry, the hypotenuses have different lengths because 3 times square root 2 is not equal to 5 times square root 2, okay? So, but measure in algebra is generic, and we attempt to describe all lengths using the abstract unit. It can, however, be proved that square root 2 has no exact measure in algebra, meaning it cannot be measured by the abstract unit. Did you get that? There is no measure for square root 2. So the symbol that you see, square root 2, is a symbol for the magnitude and not the number. By the way, to be a number, it must be rational. There is no such thing as an irrational number. It's a very ill-formed definition. We never define concepts by attributes they lack. I mean, if you say it's an irrational number is something that is not an expression of two integers, a gorilla could be an irrational number. All right. Now, what is Euclid actually saying in Book 7? First, note that in the previous books, beginning with Book 5, ratios of magnitudes and their proportions were explained in much detail, always using the geometry of line segments. Okay, so for example, a ratio is simply a comparison of two homogeneous magnitudes. In other words, here the homogeneous magnitudes are distances or lengths. Okay, that's what they are. And the one that appears before the colon is called the antecedent. The one that appears after the colon is called the consequent. Okay, and none of these above ratios, A, B, or C, are considered to be numbers unless their antecedent and consequent parts have a common measure. So this here actually graduates to the number 1/2, because we can use one of these two equal parts to measure the antecedent. Similarly here, this is 2. We can measure the antecedent using the consequent. It doesn't matter whether it's the whole of the consequent or equal parts of the consequent. It's one of the two. It's either equal parts or the whole consequent. And over here we have 3/4, because we can use 3 of the equal parts to measure the antecedent. And so when it graduates and becomes a number, we write it as P stroke Q or P over Q, as we see over here, okay? Or P over Q. So square root 2 is not a number because it cannot be expressed as a ratio of two magnitudes with a common measure, okay? With a common measure. Both both the consequent and the antecedent must have a common measure, and they do in this case. It's just either one of these short lines, all right? So any ratio P colon Q has two parts, as I've just explained, an antecedent and a consequent. So if they both have a common measure, then we can write P over Q or P stroke Q as the name of the measure. We call the name a number. That's how we realize numbers, okay? So we take ratios, check if they have a common measure, which in the case of algebra is the abstract unit, and if they do, then we give them names, okay? So as I've shown you, this here is a ratio, and it has the name in algebra, which we refer to as a half, okay? Or as 1 stroke half. A number, and here's the first ever definition of number, contrary to what that fool Clement said in his article. It can be well defined, and I've done it. A number is the name, the name given to a measure, excuse me, that describes a magnitude. So now algebra makes no distinction between a half and 2/4, okay? They're the same in algebra. However, in geometry, the ratios, this ratio and this ratio, are in proportion, but the lengths, this length and this length, are not equal, so that their measure is not the same, because the consequents are different units. These are the consequents. this consequent is not the same as this consequent, okay? And we always use the consequent or parts thereof to measure the antecedent, right? In algebra, the measure is the same. Both measures are 1/2. If you measured this length with this, the result would be 1. And if you measured this with the other consequent, the result would be 1/4. And as you can see, 1 is not equal to 1/4. So what about those ratios whose antecedent and consequent parts have no common measure? Let's see some examples. In any right angle isosceles triangle, the ratio √2 is equal to the ratio of the hypotenuse to the leg. But you cannot write hypotenuse over leg because neither of these have a common measure. Okay, there's nothing as a part of the abstract unit or the abstract unit itself which measures both. In any circle, pi is equal to the ratio of the circumference to the diameter, but pi is not equal to the circumference divided by the diameter because you cannot measure the circumference with the diameter, and there is nothing else that will measure both the circumference and the diameter, and these things are easy to prove. So neither pi nor √2 are numbers. They are merely symbols for incommensurable magnitudes. There are no numbers that describe the measure of these magnitudes. So I hope I've given you some more background and some more deeper insight into the meaning of number, okay? A number is the name given to a measure that describes a magnitude or a size. Okay, much later, homogeneous magnitudes, non-homogeneous ratios came along, so we could do things, calculate things like speed, density, etc. And all those turn out to be numbers if and only if both the antecedent and consequent parts have a common measure, in which case they graduate to a numerator and a denominator as part of fraction. Every number is a fraction. Even whole numbers are fractions. How do we name whole numbers? They're composed of units, aren't they? So we call a unit the standard, and two of those together also is written as a ratio 2 to 1, which graduates to the number 2, and we just drop the vinculum over 1 because we refer to them as whole numbers. We know automatically if we just see 2 that it means 2 units, and we treat 1 as the consequent or the standard of measure. So that's pretty much it. Much later, set theorists try to drop these foundations, which are the most rigorous, 100% rigorous. And I'll have you know that in Greek mathematics, there are no axioms or postulates. That's been a lie that's been propagated by the morons of the last, 200 or so odd years. There are no axioms or postulates in Euclid's Elements. The 5 requirements are not axioms, and they can be derived systematically. And so I'll place, once again, a link to that proof as well, which is a presentation of 28 pages. And also, I'd like you to download my free ebook on calculus. The first rigorous formulation doesn't contain any ill-formed concepts like infinity, infinitesimals, and the rot of limit theory. None of that garbage, okay? It's all based on well-formed concepts, which are geometry. The well-formed geometry of the ancient Greeks. So what I've given you today is important information because the most important concept or object in mathematics is the concept of number. So I'm running out of time. Subscribe to my channel if you haven't already. Spread the news of this channel. And hopefully I'll be able to produce more videos. I'm hoping to do another video on physics pretty soon. So that's pretty much for it now. This is the new calculus channel. I'm John Gabriel. Till next time, goodbye, folks.